Yeah, so very good morning, dear students. This is our fifth session, and just a quick recap of what we were discussing last session. We made a beginning with haloalkanes and haloarenes, and we checked out the synopsis part of methods of preparation. Prajwal, mute ಮಾಡಬೇಡಿ. One second, I'll be doing it. Yeah, it's done. You can also disable participants annotation. One can disable participants annotation.
I don't option here, sir.
No, it's not showing to me as well. Imtiaz sir, if you can hear me. Participants annotation should be disabled. Okay, we'll continue with the class till he comes back. Okay, yeah. So we have checked out the synopsis part of methods of preparation of both haloalkanes and haloarenes, where we looked at some of the common methods of preparation like converting alkenes into haloalkanes by the use of hydrogen halides, phosphorus-based reagents, thionyl chloride, and we also checked out two methods of preparation of haloarenes. One was Sandmeier's reaction, and the other one was direct halogenation. Okay, and we solved a couple of questions as well in the haloalkanes haloarenes worksheet. Today we'll continue with that further with methods of preparation as well as chemical properties. And at the end of the session, if the chapter is complete today, I'll be sharing this PDF document like how I've shared it for the previous other two documents. Okay. Now let us take up question number 6, which is also related to your method of preparation. Okay. Question number 6. I think one of Prajwal, ಯಾರೋ ಆಡಿಯೋ ಮ್ಯೂಟ್ ಮಾಡ್ಕೊಂಡಿಲ್ಲ, ವಾಯ್ಸ್ ಓವರ್ಲ್ಯಾಪ್ ಆಗ್ತಿದೆ ಇನ್ನೊಂದು ಕ್ಲಾಸಿಂದ. Yeah. Question number 6. Here you have an alkene made to react with a halogen acid, Hi, and you have to predict what the product is. Okay, let me see if I'm getting any chat responses here. Okay, B is suggested, A is suggested. Okay, good. Okay, A and B are the two options suggested. Let's verify. See, the background for this question is reaction of Hi, a halogen acid, with an alkene. Okay, now this alkene here is an unsymmetrical alkene, RCH double bond CH2. Okay, an unsymmetrical alkene. Unsymmetrical. And we know addition of halogen acid to unsymmetrical alkenes is governed by Markovnikov's rule. It is Markovnikov's addition. Markovnikov's addition, according to which the positive part of the reagent goes to the carbon of the double bond with more number of hydrogens. So the second carbon, if we number it as 1, 2, the second carbon will take up iodine and you get 2 iodo compound. And the first carbon takes up hydrogen. This is the essence of it. Okay. Now the given alkene. First, we need to decide whether it is a symmetrical alkene or an unsymmetrical alkene. It is an unsymmetrical alkene. How do you find that out? Please check this. Okay, let me show it in a different color altogether. Yeah. See, concentrate or focus on the carbon-carbon double bond. On this double bond, let me number it 1. You have a methyl group. On the other double bond, there is no methyl group, which means the chemical environment is not same. It's not symmetrical. Hence, you say it's an unsymmetrical alkene. Unsymmetrical. And which means that the given reaction here is in accordance to Markovnikov's addition, according to which H, positive part of the reagent, will add on to the carbon of double bond with more number of hydrogens. Which carbon has more number of hydrogens? It is this carbon. Let me show it to you. Yes, it is this carbon which has more number of hydrogens. See this? It has more hydrogens now. So H goes to that carbon. Hence, iodine would come to the other carbon atom where CH3 is attached. CH3, and this is where iodine gets attached. This would be the product. So all of you who have marked option B, you are right. Option B is the answer. Option A can never be the answer because this is addition reaction, not nucleophilic or free radical substitution reaction. Okay. So double bond should be removed in the product. Okay. In fact, you don't have to work all this. Straight away you can arrive at option B. How? By eliminating other options. See, this is an electrophilic addition reaction. Electrophilic addition reaction. Correct? In electrophilic addition reaction, double bond should get consumed. Double bond should no longer be present in the product. See, in all these options, A, C, and D, product still has a double bond, which means these are not products of addition, hence not the correct answer. Which is the only option where there is no double bond? Option B. This logic itself is enough for you to arrive at the correct option, option B. Okay. So dear students, in your entrance exam, you can also use this approach of eliminating options. That saves a lot of time. Okay. But this is a detailed solution for it. This is the product. Okay. So now we'll move on to the next question. Just a second. Yeah. Question number 7. Please mark this as an extremely important question because we are going to learn a very important topic or concept here. Very, very, very important, especially in exams like NEET. Okay. Yes, there is an alkene given. Of course, like the previous example, this also is unsymmetrical. Unsymmetrical alkene. It's an unsymmetrical alkene. Okay. I am straight away getting chat responses as answers. Let me see. Okay. Majority of you are pointing out B. Some of you are suggesting C as well. Okay. Some of you are suggesting C. I would like to hear from you. Those who are suggesting C, do you have any valid reason? Can you type the reason as well? I saw many of you suggesting C. Let me see if one of you can point out the reason why they are going with C. Anybody? Very good. Vishwanath Adiga says it's due to methide shift. Excellent. Excellent. Good. Let me see. Okay. Nitya says tertiary carbocation. Yes, methide shift. Very good. So all of you have caught the point here. Okay. Yes. This question is related to this very, very important concept associated with carbocations. Carbocation rearrangement. Carbocation rearrangement. That's a very, very important idea. So in whatever organic reaction you come across a carbocation, please be alert with respect to carbocation rearrangement. Okay. Now take for example this question itself. This was the alkene given, CH3, C, CH3. Then you have CH3 here, CH double bond, CH2. Now, how do we normally answer this question? We would blindly apply Markovnikov's rule. How would we do that? H goes to first carbon atom, carbon 1, and we would say Cl goes to second carbon atom. And we would predict this as the product. CH3, C, CH3, CH3, then CH, Cl. We would predict chlorine going to second carbon and hydrogen going to the first carbon. And that's the reason why 8 out of 10 of you, majority of you, almost 80% of you suggested B is the answer because we directly, blindly applied Markovnikov's rule. Remember, Markovnikov's rule is just a shortcut. It's not the reason. the actual reason behind these products that you get is carbocation as intermediate. Okay, and whenever carbocations are formed as intermediates, they can undergo rearrangement. Let me now suggest that. Let me now describe that. Okay, so this product would be wrong. This product or this route would be wrong. In that case, what would be the correct reason? Let me just show that solution to you. Okay. Request participants to turn off your video. That will take up a lot of data at your end. Okay. Now look at the solution for this. Why option B is not correct and why is option C right? Okay, check this out. CH3, 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 CH double bond, CH2. Just a second. CH double bond CH2. Okay. Now this reacts with HCl, pi electrons attaches to H, electrons going towards chloride, and C the carbocation you get here. CH3, C, CH3, CH3, CH3 here, and this is CH with a positive charge. This is secondary carbocation. This is secondary carbocation. Okay, and we all know the stability order of carbocations. What's the stability order of carbocations? Carbocation stability order. Carbocation stability. It is tertiary greater than secondary greater than primary. Okay. Yes. Now this is a secondary carbocation. Now given an opportunity, a secondary carbocation would rearrange to a tertiary. And how would that opportunity arise? That opportunity arises by one of the adjacent methyl group shifting along with its shared electron pair. It doesn't come out as CH3 plus, it comes out as CH3 minus. Hence, you call this as 1,2 methyl shift. Not methyl, but methyl shift. Because it's coming out as an anion, carbanion, methyl shift. So what's the consequence of this? See, you get CH3, carbon, CH3. Now this carbon, please focus on the pointer there. This carbon has lost its electron, therefore that gets a positive charge now. And the adjacent carbon, which originally had the positive charge, will now be attached to the methyl group, CH3. And you'll have H and CH3 as it is. This is now a tertiary carbocation, more stable tertiary carbocation, which will obviously be attacked by Cl minus. Cl minus is going to attack it, and hence you would get the product C as the answer. Okay, yes, right. Prajwal, ಕೇಳಿಸ್ತಾ ಇದೆಯಾ? hear me. ಇವ್ರಿಗೆ ಟೆಕ್ನಿಕಲ್ ಟೀಮ್ ಅವ್ರಿಗೆ ಹೇಳಿ, DSC ಅವ್ರಿಗೆ ಸ್ಟೂಡೆಂಟ್ಸ್ ವಿಡಿಯೋ ಆಫ್ ಮಾಡಕ್ಕೆ ಹೇಳಿ, ಅವ್ರು ಸೆಟ್ ಮಾಡಿಲ್ಲ ಅದನ್ನ. ಸ್ಟೂಡೆಂಟ್ಸ್ ಕಡೆಯಿಂದ ವಿಡಿಯೋ ಆಫ್ ಮಾಡಿಸ್ಬೇಕು.
ವಿಡಿಯೋ ಒಂದೇ ಇಲ್ಲ ಸರ್, ಇಲ್ಲಿ ಇದು ಪ್ಯಾನಲ್ ಲಿಸ್ಟ್ ಬರ್ತಾ ಇಲ್ಲ.
ಅವ್ರಿಗೆ ಹೇಳಿ ಅದನ್ನ ಸೆಟ್ರೇಟ್ ಮಾಡಕ್ಕೆ ಹೇಳಿ. Yeah, that was question number 7. Now coming to question number 8. So I'll just pause for a couple of seconds for question number 7. You can write it down. This is very important. Okay, now we'll go to question number 8. Yes. This is again a question on addition of halogen acid to alkene. You have an alkene here, again unsymmetrical alkene. Unsymmetrical. made to react with HBr, but remember this is in presence of peroxide. Okay, so with HBr and peroxide, with HBr and peroxide, you know what route the reaction takes? The reaction goes via anti-Markovnikov addition. Anti-Markovnikov addition. Okay, I'm getting a lot of answers as a response. Anti-Markovnikov addition. Yes, let me see. What are the answers? Yes, all of you have predicted B as the answer. Very good, very good. Let's check it. So, when you apply anti-Markovnikov's rule, which does the opposite of Markovnikov's addition, here you attach H to carbon with less number of hydrogens. Just the opposite of what you do for Markovnikov's. Okay, here you attach H to carbon with less number of hydrogens of the double bond, and Br to that carbon atom of the double bond with more number of hydrogens. Now, here, let's see which is the carbon atom with more number of hydrogens. Just a second. Yeah. Look at this. Carbon 1 has more number of hydrogens. Carbon 2 has less number of hydrogens attached to it. Therefore, Br would get attached to carbon 1. And see in which option you have Br attached to carbon 1. There are two such options. Option B, option C. Okay. But why would we go for B? Because the reactant has a benzene ring. Okay. And that benzene ring must be unharmed, unaffected in the course of the reaction. And that's the reason why you have to go for option B. Benzene ring is intact and bromine is attached to first carbon. So that's good. That's the correct reason. Okay. So this is the solution for question number 8. Anti-Markovnikov addition. Yeah. And remember, anti-Markovnikov addition goes via free radical. It's a free radical addition mechanism. Free radical addition mechanism. Okay, right. Next, let us go to question number 9. Okay, so there are 3 questions in one slide. Easy. Chlorobenzene can be prepared by reacting benzene diazonium chloride. All of you can recognize benzene diazonium chloride. This is benzene diazonium chloride prepared from aniline N2 plus Cl minus. Good. Okay. I'm getting in great chat response. Let me check your answers. Yes. Unanimously, all of you suggest B. Very good. Very good. Can anyone name the reaction? Can anyone type in the reaction? Name? Let me see. Sandmeyer's. Yes. Yes. Very good. Very good. Sandmeyer's reaction. Yeah. So in Sandmeyer's reaction, you have benzene diazonium chloride made to react with cuprous chloride in presence of HCl. That gives you chlorobenzene with nitrogen gas being evolved. That's the driving force for the reaction. Stable nitrogen gas being formed is the driving force. Good. Okay. So question number 9, straight away it's easy. Option B. No doubt. Now come to question number 10. Direct iodination of benzene is not possible. Direct iodination of benzene, something like say benzene made to react with iodine. You can't expect iodobenzene straight away in good yields. Iodobenzene HI. This usually happens when you take any halogen, chlorine, bromine. It should give you chlorobenzene, bromobenzene, and the corresponding halogen acid. But with respect to iodine, this reaction is reversible. Yield is not great. Okay. Why is that the reason? Let me see. What is your answer? Okay. You have suggested all options from A to D, which means here the audience have no clarity. So I need to elaborate on this. Okay. Okay. Right. So let's say why this reaction becomes reversible. Very important. Let me show that to you now. HI is a strong reducing agent. Never forget that. Okay. HI is a strong reducing agent. strong reducing agent. So the strong reducing agent HI reduces iodobenzene back to benzene. Okay, that's the reason why reaction becomes reversible. So the correct option here would be option B. The product iodobenzene formed is reduced to benzene by HI because HI is a very strong reducing agent. Okay, reduces iodobenzene to benzene. Reduces C6H5I to C6H6. Madam who is co-host, I have a request, madam. Madam from DSU who is hosting this class, can you please ask the tech team to stop the video of the audience?
Sir, ನಾನು ಹೇಳಿದೆ ಸರ್.
ಹಾ.
ಅದು ನಮ್ಗೆ ಹೇಳ್ತೀಯ, ಬಟ್ ನಮ್ಗೆ ಸ್ಕ್ರೀನಿಂಗ್ ಎಲ್ಲಿದೆ ಸರ್? ಅದು ನಂಗೆ ಗೊತ್ತಾಗ್ತಿಲ್ಲ ಆಪ್ಷನ್.
ಇಲ್ಲ, they have to look at the setting.
ಅವರಿಂದ ಸ್ಟಾಪ್ ಮಾಡಿ ನಿಮ್ಮ ಇದನ್ನ ಅಂತ ಹೇಳಿದ್ರು. ವಿಡಿಯೋ ಮಾಡಬಹುದು.
ಸೆಟ್ಟಿಂಗ್ ಮಾಡಬೇಕಾದ್ರೆ they should have given it. ಈ ತರ ಹೈಡ್ ಪ್ಯಾನಲಿಸ್ಟ್ ವಿಡಿಯೋ ಅಂತ ಕೊಡಬೇಕು.
Yes, sir.
Yeah. Right. Let us now go to question number 11. Question number 11. It's a question based on physical property. Okay. Question based on physical property. Which one of the following has the lowest boiling point? Which has the lowest boiling point? Remember two things. Boiling point is proportional to molecular mass. Boiling point proportional to molecular mass. Molar mass. And for a given R group, boiling point varies like this. RF lower than RCl, lower than RBr, lower than Ri. So this is the boiling point order for a given R group. So if R group is same, then iodide will have the highest boiling point. Okay. Now let's check out the answer. In the meantime, let me see what your response is. Okay, A is what is suggested by majority of you. Correct. A is the answer. Yes. See, you're asked which has the lowest boiling point, which means look for a compound with the lowest molecular mass of all. Look at option B, C and D. Look at option B, C and D. All these have two carbons. They are ethyl groups. Option A is a methyl group. Option A is a methyl group. So that should have the lowest molar mass. And moreover, in option C and D, you have bromine and iodine. Bromine and iodine will obviously have a greater atomic mass than chlorine. So that makes option A, chloromethane, the compound with the lowest molar mass and hence least boiling point. Least boiling point due to low molar mass among all options. Low molar mass among all options. So option A is right.
Karthik, off the video.
Okay. Yes. This is about question number 11. Next. That's about MCQs on methods of preparation and physical properties. Now we'll take up chemical properties of haloalkanes. Okay, another important section. We all know one very important and a typical reaction of haloalkanes is the fact that they undergo nucleophilic substitution reactions. That's the typical reactions of haloalkanes. Okay, nucleophilic substitution reactions. Yeah. So in a nucleophilic substitution reaction, you know what happens? A nucleophile attacks the carbon atom with the halogen atom and drives out the halogen atom as highlighted on this is called a leaving group. So haloalkanes typically show this category of reaction. And we know that nucleophilic substitution reactions can take place in one of these two very important mechanisms. One is called SN1 mechanism, and the other route or other possibility is called SN2 mechanism. These are two very popular mechanisms. You have studied them in detail for your board exam. Okay, so let's now revise those concepts related to those mechanisms, SN1 and SN2. Very simple. SN1 mechanism is a two-step process. It follows first order kinetics, and step 1 involves formation of carbocation. Check this out. It forms a carbocation. This is the slowest step of the two steps, hence you call it the rate determining step. And accordingly, rate equation will have rate dependent only on the concentration of the haloalkane. So it's first order. So how do I write the rate equation for this? R is equal to K into molar concentration of haloalkane alone. Yes. And later on, carbocation is attacked by nucleophile in the second step, which is a fast step. Yes. That is the SN1 mechanism. Now, coming to SN2 mechanism, the other possibility. Now, unlike SN1, SN2 is a single step process. Single step. No intermediate. Remember, in SN1, there was carbocation intermediate, and SN2 mechanism involves a transition state. A transition state. Very important. Okay. And this follows second order kinetics, which means rate of reaction depends not only on the concentration of the haloalkane, it also depends on the concentration of the nucleophile. Second order reaction. Good. Now, in addition to SN1, SN2 mechanisms, you must be aware of these two systems. Very important. This is very important. Okay. They are allylic and benzylic halides. Allylic and benzylic halides. Okay. Now, what kind of alkyl halides are allylic and benzylic halides? They are primary allylic and primary benzylic. Let me show the structures. Yes. See, this is a primary carbocation, primary allylic carbocation. This is a primary benzylic. What do you mean by allyl system? Carbon atom attached to a carbon-carbon double bond is allyl system. What is benzyl system? Carbon atom attached to a benzene directly is a benzyl system. Okay. Now please have a look at this. These are all primary carbocations because the carbon with positive charge has two hydrogens here. And here as well, carbon with a positive charge has two hydrogens. Okay. Yeah. Though they are primary, they do not, or they are less likely to undergo reaction via SN2 for allyl and benzyl halides. Important. For allylic and benzylic halides, the mechanism is SN1 predominantly. It mainly follows SN1 mechanism. Important. I'll tell you why I am stressing on this so much. The moment we come across a primary alkyl halide, we straight away come to the conclusion that SN2 mechanism is likely. But these are special cases. Allylic and benzylic halides, though they are primary, they still undergo reaction via SN1. And you know what's the reason? That's because of this. Allylic and benzylic carbocations. Allylic and benzylic carbocations are stabilized by resonance. Very important point. Allylic and benzylic carbocations stabilized by resonance. See, I can write the resonance structure for this. The positive charge sits here. CH2, H. Positive charge is on this carbon atom. Single bond, double bond, CH2. See, because of resonance stabilization, though they are primary, these carbocations are formed and the reaction goes via SN1 mechanism. Please remember this, very important. Allylic and benzylic halides. Okay, next. Let's proceed. Yeah, this is just a table or a chart to differentiate between SN1 and SN2. Some of it we have already discussed, first order, second order. SN1 mechanism is favored by polar protic solvents, very important. That's why I've highlighted it in red font. Polar protic solvents. Which are all those polar protic solvents? Water, alcohol, acetic acid, liquid ammonia, all these are polar protic solvents. Whereas SN2 is favored in a solvent called polar aprotic solvents. These are solvents like acetone, DMSO, DMF. DMF stands for dimethyl formamide. Dimethyl formamide. DMSO stands for dimethyl sulfoxide. Okay, all these are important. Then carbocation intermediate in SN1, no carbocation in SN2. Order of reactivity, extremely important. What's the order of reactivity in SN1? Tertiary greater than secondary greater than primary. This is because of carbocation stability. This is on account of carbocation stability. Okay. Whereas in case of SN2, it's reverse. Primary greater than secondary greater than tertiary. This is because of steric hindrance. Steric hindrance. Okay. And then obviously SN1 is not disturbed too much by nucleophiles. Weak nucleophiles favor SN1, whereas strong nucleophiles favors SN2. And this last part, hold on to it. I'll not discuss it now. We'll come back to that last part again. Okay. We'll come back to that last point again. These are main differences between SN1 and SN2 mechanisms. Okay. Right. Now, let us take up multiple choice questions related to these concepts we have discussed so far. Okay. Right. Now, question number 12. Propane nitrile. Propane nitrile may be prepared by heating which of these? Okay. Now, first of all, you should correctly figure out what is propane nitrile. If you don't figure that out, then you're in trouble. Okay. Propane nitrile. I think I've told this to you before as well. Whenever you are naming organic compounds in which the functional group also has a carbon atom. Okay. Please keep in mind, I repeat, whenever a functional group also has a carbon atom in it, please don't ignore that carbon atom while numbering the chain or while considering the root word. Okay. So if the given compound is propane nitrile, root word is prop. So it must be CH3, C, CH2, C triple bond N. This is your nitrile group. So nitrile group also has a carbon atom in it, right? So while naming it, you should include the carbon of the nitrile group as well. Common mistake made by students is you ignore that and you write one more extra carbon. Okay, thinking that is propane nitrile. No, what you would be getting after writing one more extra carbon is butane nitrile. So please don't make that mistake. Okay, so this is propane nitrile. Okay. Nitrile. Now you have to figure out how is this propane nitrile prepared. Now you can look at the options to get some clue. Okay. In all options, KCN is common, which means cyanide ion is acting as a nucleophile. Cn minus is the nucleophile. Yes, which means this must be a nucleophilic substitution reaction. Nucleophilic substitution reaction. Okay. Yes. There are two categories of compounds given. Alcohol is given and an alkyl chloride is given. Now between alcohols and alkyl halides are the best candidates for nucleophilic substitution because halide ion is a very good leaving group. So haloalkane RX readily undergoes nucleophilic substitution. Readily undergoes nucleophilic substitution. What's the reason for it? Because halide ion is a very good leaving group, X minus. Good leaving group. Remember all these points. In alcohol, what would be the leaving group? OH minus. It's a bad leaving group. Therefore, alcohols cannot be used in this reaction. So ruled out. Option E is ruled out. Option B is also ruled out. Okay. So we know the answer is either option C or option D. Then how do you figure that out? Very easy. See, what you want is propane nitrile, which has 3 carbons. CH3, CH2, C triple bond N. This is what you want. Okay. And cyanide ion is the nucleophile. Please observe, cyanide ion also has carbon atom. So one of the carbon atom for this compound is brought in by the cyanide ion itself, which means the reactant alkyl halide should have just 2 carbons. Okay. Why the reactant alkyl halide should have just 2 carbons? Because 1 carbon is already brought in by cyanide ion. And totally in the product, you require only 3 carbons. 1, 2, 3. That's a simple logic. Okay. So which is the option with 2 carbons? It is option D, ethyl chloride. So if you use ethyl chloride, CH3, CH2, Cl, you'll have cyanide ion attacking this and chloride leaves, hence you get this as the product. Okay. Okay, so very important question. Question number 12, option D is the answer. I'm sure all of you would have suggested option D itself. Yes, okay. Mohan has a query. Can you tell that thing about alcohol again? Yes, I can do it. Why alcohols cannot undergo nucleophilic substitution is, see, in an alcohol, ROH, if you use ROH, then leaving group would be OH, okay, OH minus. OH minus is bad at coming out. It's a good nucleophile. A good nucleophile is very good in attacking the reagent, okay? But OH minus, because it's a good leaving group, because OH minus is a good nucleophile, it is hesitant to come out. So you say it is a bad leaving group. If OH minus is hesitant to come out, then there is no question of another nucleophile displacing it. Okay, therefore alcohols are not so good in undergoing nucleophilic substitution. But if you have to carry out nucleophilic substitution of alcohol, you can carry it out by converting OH minus, a bad leaving group, into a good leaving group. If you convert OH, a bad leaving group, into a good leaving group like water, then you can carry out nucleophilic substitution reaction. Okay, yes, keep that in mind. Question number 13. Ammonia reacts with excess of ethyl chloride. This is again a nucleophilic substitution reaction where ammonia is acting as a nucleophile. See, ammonia is a nucleophile. And this is a nucleophilic substitution reaction. Nucleophilic substitution again. Okay, let's now try to understand this. So how would the reaction proceed? One second. Yeah. First, let us take up the nucleophile ammonia. Ammonia is a nucleophile because of its lone pair. Let's say it reacts with RX, a normal haloalkane. Okay, lone pair attacks the carbon with halogen. Halide ion leaves, and the leaving halide ion, observe it carefully, X minus takes away one of these proton, acidic proton, and comes out as HX. So HX is the byproduct. And what's the main product? This R group is now attached to NH2, not NH3. Why? The hydrogen atom is abstracted by X minus. This is a primary amine. Okay, just like how you have primary, secondary, tertiary alcohols, primary, secondary, tertiary alkyl halides, you have primary, secondary, and tertiary amines based on the degree of substitution on the nitrogen atom, not on carbon, based on nitrogen atom. Okay, we'll be studying this again in amines chapter, right? So one R group attached to nitrogen, it's called primary amine. Okay, now dear students, comes an important aspect, very important aspect. Reaction won't stop at this because primary amine also has a lone pair. Okay, that further reacts with excess of haloalkane if present. If you have taken excess haloalkane, this lone pair will further attack our second R group. Again, same story repeats. X minus moves out and takes up one H plus. HX is the byproduct. And see what you get now? RNH. And you have one more R group coming in. So two R groups attached to nitrogen. This becomes a secondary amine. More substitution, secondary amine. Okay. Right. Again, will the reaction stop? No. The lone pair of nitrogen is still active. In fact, it's more active now. This takes up or reacts with third mole of RX. See this? To give you RNR. Three R groups attached. This becomes your tertiary amine. Tertiary amine. Okay, I'm getting in a lot of chat responses. Okay, let me see who is with the correct answer. Okay. So some of you suggested A, D, even C. That means there's no clarity. Let me check. Yeah. So you get a tertiary amine, right? Yeah. Now, does the reaction stop? Let us ask this question. No, because this lone pair is still active. This lone pair is still active. Now, this will again react with one more mole of RX, alkyl halide, to give what is called as quaternary ammonium salt. You get quaternary ammonium salt. Now, please notice I have not written HX. No HX written here. See? Because there is no hydrogen for nitrogen to lose. Nitrogen has no hydrogen to lose. Okay? So this is quaternary ammonium salt. Okay, now let us look at the condition in the question. The condition in the question says excess of alkyl halide. Alkyl halide is taken in excess, which means we are bound to get a quaternary salt. We are bound to get a quaternary salt. Since the alkyl halide is ethyl, I will replace R with ethyl. I will replace R with ethyl. So it is C2H5 N C2H5 4 times. C2H5, C2H5. Wherever there is R, I'll replace it with C2H5. Because in the given question, you have ethyl chloride. So this is tetraethyl ammonium chloride. Tetraethyl ammonium chloride. Yes, option C is right. Option C is right. Okay. Again, mark it as an important question. Good. Hope you all have taken this down. Right? Question number 14 now. Next question. Yes. There is a reaction given to you. Let us see what the reaction is. 1 second. Yeah. The reaction C2H5Cl plus OH minus gives you C2H5OH plus Cl minus. A typical nucleophilic substitution reaction. You are supposed to find out which mechanism is followed. I think there will be no student here who will not be answering this. You can't expect a question easier than this. Yes, B. All of you are answering B. Yes, no doubt. No doubt. This is a primary alkyl halide. This is a primary alkyl halide. Hence, primary alkyl halides undergo nucleophilic substitution reaction, typically via SN2. No doubt. Okay. So option B is the answer. That was easy. Question number 15. Now think about this. Which of the following compound undergoes SN1 faster? Send in your response. Remember order of reactivity for SN1? Order of reactivity. Okay. Let me look at the responses. I got 34 responses in just 2 seconds. Very good. Okay. C is suggested. C. Yes, yes. Majority of us suggesting C. Okay. We'll check that. We'll check that. So what's the order of reactivity of alkyl halides? It is tertiary greater than secondary greater than primary. So let's mark or classify the given options. Option A is a primary alkyl halide. Option B is a secondary alkyl halide. See, chlorine is attached to carbon, which in turn is attached to 2 alkyl groups or 1 hydrogen. 1 hydrogen. Here there are 2 hydrogens. Secondary. Option C is tertiary. Option C is tertiary. Option D is again secondary. So which comes first in the reactivity order? Tertiary. Which is tertiary here? Option C, no doubt. Option C is the correct answer. That was again an easy question. Okay. Next. We'll proceed further. Okay. Question number 16. Question number 16. Which of the following compound undergoes SN2 mechanism faster? Undergoes SN2 mechanism faster. Okay. Now there is dear students, there is a small change you need to make. Apologies from my side. Shift this CH3 here. It's a printing error. This CH3 should be here. Okay. Now please try to give the answer. Let me see. What are the responses? Okay. C is suggested. Majority of you. C is suggested. Okay. But one of you suggest A. Okay. Sklita. I'm sorry if I pronounced it wrongly. Yeah. Sklita suggests A. Or I didn't see properly. Okay. Yeah. So it's not one option you're suggesting, all of you. So that means this requires discussion. Let's check it out. Okay. The mechanism asked here is SN2, right? We know that the order of reactivity in SN2 is order of reactivity for SN2 is methyl halide greater than primary, greater than secondary, greater than tertiary, right? So we'll have to look for primary alkyl halides because that's what is more reactive, because methyl is not there here. Okay, now which are the primary ones? Option A is primary. See, bromine is attached to a carbon with 2 hydrogens. Option A is primary. Option B is also primary. Bromine is attached to a carbon with 2 hydrogens. So now we are in a dilemma, a fix, because 2 options are primary here. Option C is tertiary, so hence ruled out completely. Option D is also tertiary, ruled out completely. So our choice has to be between A or B. Now, how do we decide between A or B? Both are primary. Okay, please check out option A. Option A has, and rewrite it, CH3, CH, CH3, CH2, CH2Br. Okay, this is option A. Whereas option B is CH3, CH2, CH, CH3, CH2Br. Now please observe, this methyl group is a big obstruction. It occupies space, it offers hindrance or obstruction. Now, in which case CH3 is closer to the carbon having bromine? In option B. Here, therefore, because of the CH3, there is more crowding or hindrance. Whereas here in option A, the obstruction or hindrance is less steric hindrance. Less steric hindrance. Now we all know the criterion for SN2 mechanism is steric hindrance. So which has the least steric hindrance between A and B? It is option A. Option A is the answer. Mark it as an important question because though both are primary, even among primary halides, you can decide the reactivity order based on their bulkiness and steric hindrance. Okay. Yes. Question number 17 is again a cakewalk. Very easy. SN2 mechanism proceeds through the formation of. I'll not even look at your chat response because I'm sure all of you would have suggested option B. Transition state. No intermediate here. Okay. Transition state. Good. Okay. That is SN2 mechanism. Question number 17. Yes. So let's see what's next. Yeah. That's about questions on chemical properties of haloalkanes, particularly nucleophilic substitution reactions. Okay. Now, one other important section under your haloalkanes chapter is this idea of optical isomerism, a type of stereoisomerism. Stereoisomerism, wherein compounds have same molecular formula, same structural formula as well, but they differ in a property called optical activity. Optical activity. I'll just tell you the basics of this and then we'll proceed further. Okay. Yeah. You can see a pair of molecules here. These are two forms of the same molecule, alanine. Alanine, you all know, is an amino acid. Yes. Now, this alanine can be represented as a molecule and an image. Okay. Mirror images. Right. And if you carefully observe it, the two images are non-superimposable. These are non-superimposable mirror images. Superimposable mirror images. Okay. And let's see, what do we call these non-superimposable mirror images as? Such a pair of non-superimposable mirror images are called enantiomers. Enantiomers. They are mirror images and they are non-superimposable. Okay. Now, why are these two non-superimposable? Because of this condition called chirality. Because of this phenomenon called chirality. Alanine, like a pair of human hands, are chiral. Now, when can you classify an object to be chiral? If it is non-superimposable over its mirror image. And how do we get to know that whether a given molecule is chiral or non-chiral? Okay. The best way to check that is to create models. As you can see, the models here, these are called ball and stick models. That's the best way. And try to see yourself whether it superimposes or not. But in an examination hall, we'll not have access to those models. Okay. So scientists have given us two indicators using which one can figure out whether a given molecule is chiral or achiral. Okay. So please concentrate on this. Very, very important. Very, very important. Okay. So to know whether a molecule is chiral or not, to know whether a molecule exhibits enantiomerism or not, to know whether a molecule is optically active or not. These are two conditions important. One, absence of plane of symmetry. There should be no plane of symmetry. And two, watch out, this is important. The compound should contain an sp3 hybridized carbon atom, sp3 hybridized carbon atom attached to 4 different atoms or groups. All the 4 groups attached must be different. Likewise, look at this alanine compound. Central carbon is there. Central carbon. See what are the groups it is attached to? Hydrogen, carboxylic acid, COOH, methyl CH3, amine NH2. All 4 groups are different. Okay. Again, here is a word of caution. A word of caution from my side. One common mistake done is you only look at one atom. Some students think, okay, here also it's carbon atom. Here it's carbon atom. Both are same. So are chiral. No, that's a wrong judgment. Don't look at individual atom. Look at the entire group. You should look at the entire group, not just one atom. If you focus only on one atom, you'll come to a wrong conclusion. Okay, both are carbon atoms, both are same, hence it's not chiral. No. So my suggestion here, please look at the entire group. Okay. Yes. That's about enantiomers, chirality, optical activity. How are the three related? If a molecule has a chiral center, it is then branded as chiral. If a molecule is chiral, then it will be non-superimposable over its mirror image, and that pair is called enantiomers. And these enantiomers have the ability to rotate plane polarized light. Rotation of plane polarized light. Plane polarized light. Plane of plane polarized light. Okay. Rotation of plane polarized light towards the right or towards the left. Accordingly, you classify isomers as dextro or levo. Accordingly, you have 2 varieties. Dextro isomer, clockwise rotation. Dextro, which is clockwise rotation. Then you have levo, which is anti-clockwise rotation. Anti-clockwise. Easy. Okay. That is basics of isomerism, optical isomerism, and these are some important properties of enantiomers. See, they differ in their optical activity, hence are called optical isomers. Optical isomers. Yes, dextro and levo. Okay, that's about optical isomerism in a nutshell. Now let's see if we can take some questions on this. Or before that, why did we study it here in haloalkanes? Because stereoisomerism can be applied to SN1, SN2 reactions. Yes. Stereochemistry of SN1, SN2 reactions. Okay. Let's apply that here. Easy. In any nucleophilic substitution reaction, there are 3 possible outcomes. One is retention, inversion, and racemization. We'll see what these are. Let's look at SN1 mechanism. Before that, see what is retention. If the nucleophile Y comes in the same position as X, same relative position as X, then you call it retention product. This is retention product. See? Nucleophile Y takes the same place as X relative to other 3. Whereas look at the other one option, the compound B. Nucleophile Y takes a position opposite to that of B. So this is inversion, reverse inversion. Okay. So you can equate inversion to umbrella getting toppled up in a strong wind. If you hold the umbrella against a strong wind, you know the umbrella gets toppled up, right? Exactly similar to that. You have X here, all these groups are facing on one side here, and these groups will be facing the other side. Umbrella getting toppled up. That's inversion. Okay. Then you may have a third case. What's the third case? A 50-50% mixture of both inversion product and retention product. This is what is called racemic mixture, and this process is called racemization. And racemic mixture is optically inactive because 50% is dextro, 50% is levo. The dextro rotation of one enantiomer is compensated, cancelled out by the levo rotation of the other enantiomer. Okay, so that's about the consequence. Now let's apply it for SN1, SN2. In SN2, what happens? Very simple. Nucleophile attacks from a side Opposite, it should have been, I should have shown it here. Okay, OH minus ion attacks from a side opposite to leaving group. Hence, have a look at this. OH has come in to a position opposite to that of Br. So this is inversion, and in particular called Walden inversion. This is called Walden inversion. Okay, next. That's the consequence of SN2. In SN1, what happens? See, please check it. Haloalkane cleaves, producing carbocation, and please remember, carbocation is planar. Planar carbocation. Carbocation is planar. And when something is planar, you know the nucleophile can approach from above the plane or below the plane. So there are two possibilities: above the plane or below the plane. If it approaches above the plane, you get one enantiomer. If it approaches below the plane, you get the other enantiomer. Since there is a 50-50 chance of either approaches, you get a racemic mixture plus enantiomer dextro as well as levo. So the stereochemical consequence of SN1 mechanism is racemic mixture. SN2 mechanism, it is Walden inversion. SN1 mechanism, it is racemic mixture. Yes. Okay, we have a couple of questions on that. Let's solve it quickly. Okay, read out the question now. Question number 18. Yeah, 1 second. Let me shift the toolbar. Okay, check out question number 18 now. Optically active compound among isomers of C4H9Cl is. Now these are all the 4 isomers of C4H9Cl. You have to find out which is optically active. Remember, for a compound to be optically active, one of the conditions, not the only condition, one of the conditions is it has to be chiral. For it to be chiral, what's the condition? There must be sp3 hybridized carbon atom attached to 4 different atoms bar groups. That's it, easy. So let me see how many of you answered it. Okay, B is what is suggested by everybody. Everybody, unanimous. Good. Good. Let's check out. Here there is a clue that you need to remember. Okay, a CH3 carbon. Please remember this clue. Very helpful. A CH3 carbon and a CH2 carbon. In a given organic compound, if you come across CH3 and CH2, these two can never be chiral centers. Never chiral centers. Okay, because you have identical hydrogen atoms here. Okay, if you have to spot a chiral center, look for CH and C, carbon with no other atoms attached, no hydrogen atom attached. These can be potential chiral centers, provided they're attached to all 4 different groups, potential chiral centers. That's a very important point. Okay, look at option A therefore. In option A, you only have CH3 and CH2. There's no CH and C, hence ruled out. It can't have a chiral center. In option B, you have CH3s, CH2s, but look at this. There is a CH. Okay, now this can be a chiral center. We'll verify. We'll see whether it is attached to 4 different groups or not. Focus on this carbon, dear students. Let me highlight it. This carbon attached to methyl group on one side, chlorine atom on the other side, hydrogen atom, and then ethyl group. Methyl, ethyl, hydrogen, chlorine, all 4 are different. And hence, yes, this is a chiral center. Chiral center is usually indicated by an asterisk mark. Therefore, all of you are right. It's option B. No doubt. No hesitation. Option B. Good. That was question number 18. Now coming to question number 19. The reaction described below is, yeah. Which mechanism is it? SN1 or SN2? Check out from the stereochemistry. Check out from the stereochemistry. Let's see what are your answers. Again, B suggested by everybody. Good, good. Walden inversion. Skilita says it's Walden inversion. Correct. Okay. So the described below reaction is SN2. How are we so sure it's SN2? Because we see Walden inversion there. Walden inversion. Walden inversion. See, Br group is on this side, whereas OH group takes a position opposite to that of Br relative to all the other three. Hence, it is Walden inversion, which is possible only for SN2 mechanism. SN2 mechanism is the one which is attached, which is associated with Walden inversion. Good. That was question number 19. Question number 20. Yes. SN1 reaction of alkyl halides leads to easy. I don't have to elaborate on this. It's racemization. That's the stereochemical consequence of SN1. Good. Now, I want you all to answer 21. Leave out 20. 20 is easy. All of you answered it. Please type in the question number and answer. Answer 21 now. Which of these factors favor? Yes, Karthik says it's option C. Steffi Sandra also agrees it's option C. Okay. Okay. Afra says option B. Okay, so there's a mixed response here. Chandu says option C. Okay, let's see. SN1 reaction is favored by which of these? Okay, remember, SN1 reaction is favored by polar protic solvents, not non-polar solvents. It's favored by polar protic solvents. Polar protic solvents. Yes. So A is ruled out. B, bulky group on the carbon atom attached to halogen atom. Let's spend some time on this. See, you all know what the order of reactivity of SN1 is. Order of reactivity is tertiary greater than secondary greater than primary. See this? This is a tertiary alkyl halide. Tertiary. This is secondary. CH3C, CH3H, Br, secondary. This is primary. CH3, CH2, Br. Please observe which is more reactive? Tertiary. Reason? Bulkiness. Look at this bulkiness. That offers a lot of steric hindrance, therefore prevents SN2. Not only that, it can stabilize carbocation well, therefore encourages SN1. So bulkier the groups present. As you go to secondary, see, it becomes less bulky. And you go to primary, it becomes much less bulky. Hence, bulky groups favor SN1. It's option B. No doubt. So please don't miss out on these easy questions. Be careful. Bulky groups are the ones which favor SN1 mechanism. Okay? Yes. Let me now go to question number 22. Okay. Let me read out the question number 22. This was a question in one of the previous year's NEET papers. Easy. Looks difficult. It looks as though some, high-end compounds are given. Not there in the syllabus. No, it's easy. Focus on the substituent. Okay. The question is, the reaction will go faster. The reaction will go faster if concentration of the nucleophile is increased. Now we have two options, SN1, SN2. In which mechanism reaction rate depends on concentration of nucleophile? It is SN2 mechanism. It's in SN2 mechanism. Rate of reaction not only depends on the concentration of the alkyl halide, but also depends on the concentration of the nucleophile. Okay, chat responses are pouring in. Let me see. Okay, D is suggested, C is suggested, B is suggested. Okay, we are in a mess again. Okay, but majority of us suggesting B. Okay, majority of suggesting B. Okay, check it out. We'll check it out. So we have now decided that it's SN2 mechanism, right? Now, what's the order of reactivity under SN2? Order of reactivity is primary greater than secondary greater than tertiary, and more greater than primary is methyl, CH3. But here methyl is not there. Therefore, let's see what category these haloalkanes belong to. Okay. Option A, see bromine attached to carbon with no hydrogen at all other atoms are carbon, so it's tertiary. Option A is tertiary, hence least in our list. Option B, yes, primary, bromine attached to carbon with 2 more hydrogens. Primary, yes. Option C is again tertiary. Option D is secondary. So which is more likely among all the three? It is primary. Primary. Therefore, that becomes the correct answer. That becomes the correct answer. Yes, option B for question number 22. Okay. Let's see if we have one more question or we'll now go to other categories of reactions. Yes, that's about questions on nucleophilic substitution reactions, stereoisomerism, and applications of stereoisomerism in nucleophilic substitution reactions. Okay. Now, apart from nucleophilic substitution reactions, haloalkanes also undergo this category of reactions called elimination reactions. And this is not new to us. We have discussed this under alkenes chapter in our attempt to study methods of preparation. Okay. There you got to know when a haloalkane is made to react with alcoholic KOH, see, alcoholic solution of potassium hydroxide or sodium hydroxide, there is elimination of both hydrogen of beta carbon and halogen. This is therefore called dehydrohalogenation. We have discussed this already. Okay. And one more point, whenever elimination gives rise to more than one product, like how we see here, elimination gives rise to 2-bromopentane, gives pent-1-ene and pent-2-ene both. But as you can see, pent-2-ene is major product of elimination, pent-1-ene is minor. Okay, what's the basis for it? It's the stability of alkenes. Okay, and this was what was first identified by another Russian called Sedzev, who generalized it as a rule called Sedzev's rule. So to predict which is a major product, the preferred or the major product in an elimination reaction, when there are more than one product, this idea becomes important. The preferred product is the one which has, the preferred alkene is the one which has greater number of alkyl groups. Greater number of alkyl groups attached to doubly bonded carbon atoms. That's it. Easy. Easy. Simply count the number of alkyl groups attached to doubly bonded carbon atoms. If that alkyl group number is high, then it is more substituted and more stable. Now take for example pent-2-ene, or for let me take for example but-2-ene. CH3, CH, double bond CH, CH3. Okay. 1 second. Let me shift it here. Yeah. This is but-2-ene and this is but-1-ene. CH3, CH3, CH2, CH double bond CH2. Okay. Now please observe, focus on the double bond. Let me highlight that. Our focus, 1 second. Yeah. Our focus should only be the double bond. How many alkyl groups attached to it? 2 alkyl groups. 1, 2. 2 R groups. Whereas see, look at this double bond. How many alkyl group? Only 1. 1 R group. So which R group is more substituted? Sorry, which alkene is more substituted? The one which has 2 R groups. This is more substituted. More substituted. Hence major, more stable. This is less substituted. Less substituted. More alkyl groups, more substitution. Simple logic. This therefore becomes minor product. Easy to understand. Okay. That's what you need to remember with respect to elimination reactions. In addition to elimination, haloalkanes are also known to react with metals. Okay. One very prominent reaction is their reaction with magnesium metal to form this very popular famous compound called Grignard reagent. Grignard reagent, RMGX, belongs to this category of compounds called organometallic compounds. Organometallic compounds. Okay. Let me see if there are any queries at this stage. No. Okay. So this is our Grignard reagent. Next. Reaction with metallic sodium. This is another popular reaction called Wurtz reaction, wherein metallic sodium reacts with haloalkane to give you higher alkane, something which we are studying for the second time. We have gone through this under alkanes. Remember, please recollect. This is something we're discussing for the second time, higher alkane. Higher alkane. That's the reason why I discuss hydrocarbons first before coming to your second year organic chemistry, because a lot of reactions are repetitive, like Wurtz reaction. Okay, so we don't have to check that out again. Yes, a couple of questions on this. Question number 23. Yeah. You have a haloalkane, 2-bromopropane. You are reacting it with alcoholic KOH. You know what kind of reagent alcoholic KOH is. Then you are treating it with HBr in presence of peroxide. You know which route the reaction takes. And then you are treating it with sodium iodide and acetone. Can anyone tell me what the product C is? These are all questions in which you are given a sequence of reactions and you are supposed to find out the final product. So to know the final product, you should find the products that you get in the preceding steps. Okay. Yes. Anybody with the answer? Chat section. Okay. Skilita again says A. She emphasizes on A. Okay. Let's see. Okay. Varun, Hariom, Purvi, all of you are suggesting it's A. Good. Good. We'll see. We'll check it out. First reaction. CH3. Just a second. CH3, CHBr, CH3. CH3, CHBr, CH3, alcoholic KOH. Okay, this is a dehydrohalogenation reaction. Halogenation. This results in an alkene. So hydrogen leaves along with the halogen. So you get an alkene, propene, CH3, CH, double bond CH2. Well and good. This is your compound A. Now what is A compound subjected to? Subjected to reaction with HBr in presence of peroxide. What kind of reaction is it? It is anti-Markovnikov addition. Anti-Markovnikov. That gives you 1-bromopropane, CH3, CH2, CH2Br. Good. Now, last reaction. Please name the last reaction, all of you. I'll be looking at a chat response. Name the last reaction, that is B to C. Which reaction converts B to C? Yes, Srinivas says Schwartz reaction. Is it Schwartz reaction? Or is it Finkelstein? Yes, Rashmika and Pallavi. It's Finkelstein reaction. Yes. Schwartz reaction is for fluorides. Again, not to get confused. Schwartz reaction is for fluoride. Finkelstein reaction is for iodide. So you get iodobenzene. Sorry, iodopropane. CH3. Again. CH3. CH2. CH2I. This is Finkelstein reaction. Finkelstein reaction. Okay, done. That was question number 23. Very good. Now let's proceed further. 24. Hope all of you got answer for this question 23. It's option A. CH3, CH2, CH2I, iodopropane. Option A is right answer. Very important question. And such sequence-based questions are increasing nowadays in entrance exams. This is your compound C. Question number 24. Yeah. An alkyl halide on reaction with sodium in presence of ether. So this must be Wurtz reaction. So this indeed is Wurtz reaction. Okay. Wurtz reaction. And the alkane is given. Product alkane is given. And from that you have to figure out what the alkyl halide is. We have already solved a question of this type in our first worksheet, organic chemistry worksheet. Okay, or sorry, second worksheet, hydrocarbons worksheet, wherein you write the structure of the alkane. It's a hexane, so I write 6 carbons, 1, 2, 3, 4, 5, 6. Then it says 2, 2. At the second position, there are 2 methyl groups. And even at the fifth position, there are 2 methyl groups. This is the product alkane. And you're supposed to figure out what reactant upon Wurtz reaction gives you this dry ether. Dry ether. Anybody with the answer? Show the chat response, please. You can suggest that in the chat response. Anybody? Let me see. Okay, all of us suggesting B, 24B. Good, good. All of us suggesting B. Okay. Now, I have already given you the plan. We have discussed this in the hydrocarbons worksheet. What should we do for such questions? Cleave the molecule into 2 equal halves. 1 second. Cleave the molecule into 2 equal halves. Then write each fragment. I separately write this fragment. Carbon attached to 4 carbon atoms. Okay. Now I need to fix a halogen here. Where should I fix it? I should fix it to that carbon atom which was originally part of the linkage. And that happens to be this carbon atom here. I put a halogen, chlorine. Yes. Now the next part is naming, by which you can also revise your nomenclature rules. Naming that carbon, or you should number it from that end, which gives lowest number for the substituent. So it must be 1, 2, and 3. So it therefore must be 1 chloro. Yes, 1 chloro. 2, 2 dimethyl. Yes, 2, 2 dimethyl propane. Perfect. Option B. All of you are right. Very good. Very good. All of you have given the correct answer. That was question number 24. Okay. Right. Now let's proceed further and see what is in store next. That's about haloalkanes chemical properties. I think we'll have to check out haloarene chemical properties. Yes. Chemical properties of haloarenes. A few important things here. Please note, haloarenes are not so good in undergoing nucleophilic substitution reaction like your haloalkanes. They are less reactive. Very important point. Now, you should also know the reasons why they are less reactive. These are the reasons. 1, because of plus R effect of chlorine. See, carbon-chlorine bond acquires partial double bond character. And you know, double bond is stronger than single bond. Therefore, bond breakage becomes difficult. Hence, less reactive. That's one reason. Second, look at the hybridized state of carbon here. In haloarene, hybridized state of carbon atom is sp2 hybridization. Something like, say, chlorobenzene. It is sp2 hybridization. So sp2 hybrid carbon atom is more electronegative, will withdraw electrons towards itself, thereby making this bond stronger, less reactive. And moreover, if at all it has to go via SN1 mechanism, it has to form a carbocation, which should look something like this, but this is unstable. Unstable. So SN1 is ruled out. SN2 is also ruled out because benzene is a rich electron system with a pi electron cloud above and below the plane. 1 second. Let me show it to you using the highlighter. Just a minute. Yes, see this? You have pi electron cloud both above and below the plane. Hence, it repels repels any nucleophile that is present. Okay, nucleophile would be repelled. This is pi electron cloud. That's it. Okay, let's see. Let's check out further. Yes, haloarenes are not so prone to nucleophilic substitution reactions, but you can force them to undergo nucleophilic substitution by making a small change structurally. What is it? 1 second. Yes, attach electron withdrawing nitro groups. Check this. Nitro groups, electron withdrawing nitro groups. And that too at what positions? Ortho and para positions only, not at meta position. Okay, because nitro group strongly withdraws electrons. Nitro group strongly withdraws electrons only from ortho and para positions, not from meta position. That's how this reaction is helpful. Okay. Now please check out these three reactions. When you have only one nitro group, temperature is 443 Kelvin. Remember the temperatures. When you have two nitro groups, you increase the nitro groups, reactivity increases. Then reaction occurs at a low temperature, 368 Kelvin. When you have three nitro groups at ortho and para positions, the reaction is the fastest. You just have to warm it. Don't have to heat it to high temperature. Important. Next. Then the routine electrophilic substitution reactions. Okay. What are all the points you have to remember for electrophilic substitution reactions? You'll have haloarenes. Okay. A halogen atom attached to benzene shows plus R, no doubt, plus R effect. But be careful. This is a very, very important point, often missed by students. Though chlorine, bromine or iodine show plus R, they are slightly deactivating. Slightly deactivating because their resonance effect is weaker than inductive. And no doubt, all these halogens are ortho and para directing. So they direct the incoming electrophile to the ortho or para positions. Ortho and para directing, easy. So what are the common reactions we study? The same old reactions, halogenation, where you get dihalo compound. Remember, para product will always be major, thermodynamically stable, more stable than ortho product because of steric repulsion. Steric repulsion minimum. Similarly, nitration, where you use a nitrating mixture, same, you get ortho nitrochlorobenzene, para nitrochlorobenzene. Likewise, you have sulfonation, where reagent uses sulfuric acid, you get sulfonic acids. And then two very popular reactions, Friedel-Crafts alkylation, Friedel-Crafts acylation. This is alkylation. This is acylation. Mind you, in acylation, you get ketones. These are ketones. Acetophenone derivative. Okay? Yes. Now, like haloalkanes, haloarenes also react with metallic sodium. And this reaction of a haloarene with metallic sodium is called Fittig reaction. Reaction of only haloarene with metallic sodium is Fittig, analogous to Wurtz reaction. But look at this reaction. Reaction of a haloarene with a haloalkane. Is sort of a combination of Wurtz and Fittig, hence you call it Wurtz-Fittig reaction. Very popular, very common reaction for your entrance exam. Yes, I think with this we complete all synopsis part of haloalkanes. Okay, now let me see how many more minutes remaining for me. Yes, I have solid 5 minutes. So let's try to pack in as many questions as possible. It depends on how well you respond. Okay, yes, first, that is question number 25. Carbon-chlorine bond of chlorobenzene in comparison to carbon-chlorine bond of methyl chloride. Okay, I'm straight away getting responses here. Let me check. Okay, Libina says, asks me to show the previous slide once again. Okay, I'll do that. And then we'll come back to it. I'll wait for a couple of seconds. Okay, not more than that. One of you asked for the previous slide once again. Okay, yes. I'll just wait for a couple of seconds. Anyway, I'll be sharing these slides to you. Don't worry. This will be shared in the website, DSU website, okay? With the solution, it will be shared. So if you can't manage to take down so fast, you can anyway refer to that later, okay? But it will be very difficult for me to give time for you to copy it down in the session. Yes. Yeah. Let me take this up for discussion now. Chloromethane. This is chloromethane, CH3Cl. Wherein carbon atom is sp3 hybridized. Then you have chlorobenzene, wherein chlorine is attached to benzene ring, wherein the carbon atom is sp2 hybridized. Very good. Okay. Now you know chlorine attached to benzene ring exerts plus R effect and shows resonance, because of which carbon-chlorine bond acquires partial double bond character. See this? Let me highlight that. One second. Let me get rid of the toolbar here. One second. Yeah. So here you have a carbon chlorine double bond, partial double bond, and we all know double bonds are stronger and shorter. If a bond is strong, then it is short. Okay. So carbon chlorine bond of chlorobenzene. One second. Yeah. Carbon chlorine bond of chlorobenzene is shorter and stronger than that of chloromethane. Yes. So it's option C. Easy. I'm sure most of you would have given this as the answer. Question number 26. Chlorobenzene on nitration gives major product. Yes, we discussed this. Chlorobenzene upon nitration, you get both orthochloronitrobenzene, parachloronitrobenzene. The reagents are concentrated nitric acid, concentrated sulfuric acid. That gives you two products, ortho substituted, para substituted, because chlorine atom is ortho para directing. Chlorine nitro here plus chlorine nitro at the para position. But you know, para product is major product when compared to ortho. Thermodynamic stability, minor. Yes. So which is the correct option? It is 1 chloro, 4 nitro. 1 chloro, 4 nitro. Now please note, why should it be named 1 chloro, numbered 1 and 4? Though either case it's same. Can anybody answer? Why is it not 1 nitro, 4 chloro? Why it isn't 1 nitro, 4 chloro, and why 1 chloro, 4 nitro? Can anyone send in the response? Yes, Pallavi, Chandana, Shambhavi, Srinivas, all of you are suggesting it is alphabetical order. Correct. To follow the alphabetical order. So it is 1 chloro, 4 nitro. Option A is right. Okay. Let me go to the next question. Question number 27. Yeah. Quickly. Which of the following compound undergoes replacement of Cl? Replacement of Cl. Okay. By OH. By merely warming with water. Okay. I'm getting answers straight away. By merely warming with NaOH. Okay. Let me see. 1 second. D is suggested. Yes, yes. D is suggested. Good. Because more electron withdrawing nitro groups, that too at the right position, ortho and para, easier the reaction is. Okay. So option D is the answer because, 1 second. Yeah. Option D is the answer because you have 3 electron withdrawing nitro groups. 3 strongly electron withdrawing. That's the word. Strongly electron withdrawing nitro groups at ortho and para positions. That's what is important here. Very good. Okay. Yes. Here again we have one more sequence based question. Sequence of reactions based question. I want all of you to figure this out. Starting from X to Y to Z. Let me see who will give the answer. Correct answer. Quickly. Yes, it's exactly 11:45. But give me 2 or 3 more minutes. I'll end the session so that haloalkanes worksheet is done. Next chapter, next class, we can take up alcohols, phenols, and ethers. Yes, please. What's the answer? For question number 28. Okay. A is suggested. Varun says you have Sadmir reaction involved. Correct? Perfect. Okay, we'll check it. The given compound is aniline. Aniline is made to react with sodium nitrite in presence of HCl. You know, that's when you get HNO2. NaNO2 bar HCl. Perfect case for diazotization. This is called diazotization. So what will be compound X? Compound X will be a diazonium chloride. Easy. This is X. N2 plus Cl minus. Now this is in turn treated with CuCl. Again, HCl is missed out. Technical mistake from our side. HCl missed out. That should be there. This is Sandmeer reaction, like one of you pointed out. Sandmeer reaction, yes. And therefore, Y is chlorobenzene. Easy. That's the product in the Sandmeer's reaction. Then, what is the reaction from Y to Z? Can anyone name it? Y to Z. Which reaction is Y to Z? Let me see. Let me check out the site responses. Yes, fatigue. Fatigue is suggested. Okay. Is it really fatigue reaction? Wurtz fatigue. Yes, yes. Chandana suggests that. Kilita Chandana suggests that it's Wurtz fatigue. Yes. See here you have haloalkane and haloarene both. This is haloalkane. And this is haloarene and this is haloalkane. So the product must be a product of Wurtz fatigue reaction. This is Wurtz fatigue reaction. And the product happens to be toluene, no doubt, easy. Option A is the answer. Very good, very good. Quickly, let us complete the other two. Yes, these are questions related to a small section in your haloalkanes chapter, and we call them polyhalogen compounds. Polyhalogen compounds, okay. I didn't cover it in the synopsis section because it's a very small section and just made up of facts. Nothing much to discuss. You just have to go through them, okay. So please go through it. Not that important because it's not been asked to so many times in the entrance exam. This can go unrepresented also. Okay, so polyhalogen compounds, right? Under that, there is a very popular compound that is DDT, an insecticide. You are supposed to know its name as well as structure for the entrance exam. Now I am going to write its structure. Please check this. I am now writing the structure of DDT. 1 second. Let me push it this side. Yeah. DDT is actually a derivative of a compound called chloral. Okay, yes, yeah. 2 carbon atoms. Okay, one of it is attached to 3 chlorine atoms. The other carbon is attached to 2 benzene rings. 2 benzene rings. Which in turn has chlorine atom at the para position. This is structure of DDT, and which name matches it? Check it out. Para prime at 2 para positions, dichloro, diphenyl, 2 benzene rings, diphenyl, trichloro, 3 chlorine atoms here, ethane, 2 carbon compound. Yes, it's option A, no doubt. Option A. Okay, right? Last question of the worksheet. Freon 1,2. Freons come under this category of compounds called chlorofluorocarbons. Chlorofluorocarbons. Freons are chlorofluorocarbons of methane and ethane. Methane and ethane. And freons are usually named by these numbers, codes. So here the first number, Freon 1,2. Freon 1,2. First number indicates number of carbon atoms. Number of carbon atoms. Second number indicates number of fluorine atoms. So 1,2 means 1 carbon and 2 fluorines. Which option here has 1 carbon and 2 fluorines? Let's check out option A. It has 1 carbon, 3 fluorines. Not the correct answer. Option B, 1 carbon, 1 fluorine. Not the correct answer. Option C, 1 carbon, 2 fluorines. Yes, this is the right answer. Option D, 1 carbon, 1 fluorine. Not the right answer. Okay. So option C is correct. Yes. So thanks a lot, dear students. So we have completed almost 3 organic chemistry chapters, 2 of first year, 1 of second year. Next session, we'll take up alcohols, phenols, and ethers. Thank you.
So close ಮಾಡಬೇಡಿ ಅಂತ ಹೇಳಿದ್ರು ಸರ್.
ಯಾವುದನ್ನ?
ಈ ಸೆಷನ್ ಕ್ಲೋಸ್ ಮಾಡಬೇಡಿ ಅಂತ ಹೇಳಿದ್ದಾರೆ.
ಅಂದ್ರೆ ಅರ್ಥ ಆಗಿಲ್ಲ, ಏನ್ ಮಾಡ್ಬೇಕಂತೆ?
ಹಂಗೆ ಬಿಟ್ಟಿರ್ಬೇಕಂತೆ.